Hi Geo H, this is Unit 3, Lesson 2, and today we're going to talk about axioms of equality. So geometry is about how objects, they can be points, lines, angles, figures, relate to each other in space. There are certain axioms about the properties of equality that hold when we look at measurements in space, specifically the length and the angle. So we need to master these in order to make certain arguments in geometric proof. Before we look at axioms of equality, we first review a most basic axiom about space. In each diagram, make a statement about the whole measurement relates to individual parts. So we did a little bit about this in Unit 1 when we were measuring things. But if I know that AFT is a line, so I'm just saying that this is a line right here. So that makes AF and T collinear. So basically I can say AF, which is the left part of the line, plus FT, which is the right part of the line, equals AT, which is the whole entire line. Okay, if I wanted to say that line segment AF plus line segment FT, and together those would be congruent to line segment AT. So if I'm talking about the length, I don't put the line segment above the two letters like on the right here, AF. If I'm talking about the line segments, then I use the word congruent. So the lengths of the lines are equal, the segments are congruent to the whole thing. Now the same thing is going on for this angle over here. So if I want to say angle SRK, which is the angle on the bottom here, SRK, see how SRK, plus angle KRN, which is the one right on top of it, angle KRN. Well, together, if you add them, they would equal angle SRN, the whole thing. If I'm talking about their measures, then I'm saying, well, actually, this should be congruent, sorry. If I'm talking about the measures of the angles, so then I'm talking about the degrees, I use the M in front of it, and then I say the measures. So the measures are equal, the angles themselves are congruent when I add them. Oops, this should be measure. And I mentioned this before, if you were to mess that up, don't really worry about it. Most of the time when we're doing proofs, we use congruent. All right, so basically the statement, how am I justifying both of these statements that I wrote up above? And that is with this, the whole is equal to the sum of its parts. So if I add the two parts together, that will equal the whole thing. So that's one of the axioms. If axioms seem obvious to you, it's because they should. It's sort of like, well, of course, that makes perfect sense. The idea of an axiom is that its truth is so obvious it does not need proving. We now continue our discussion with the axioms of equality. So in exercise 1, we're going to do the addition axiom, or we just really call it addition. And that says if equals are added to equals, the sums have to be equal. So we are given CE is equal to FE. Okay, so I'm going to mark that on my picture. CE is equal to FE. They look equal. And EB, which is this longer segment, is equal to ED, that longer segment. So we're going to do a proof for this. It says actually, let's make up a test case to make sure you understand what the given illustrates. So let's just make up numbers. So let me get a different color pen. Let's say that I'm not going to even measure it. Let's say that CE is 3 and FE is equal, so FE also has to be 3. And let's say that EB, I don't know what it is 5. And if ED is equal, then that's 5 also. All right, so if CE is equal to FE, and they both equal 3, and EB is equal to ED, they both equal 5, then the whole segment FD would have to be equal to the whole segment CB, and those would be equal to 8. That's really what we're doing in this proof right here. We're proving that equals added to equals are equal. The sums will be equal. So if two things that are equal and you add on equal things to each of them, then that sum also has to be equal. So in our proof, the statement's written and the reasons are, we're going to provide the reasons. How do I know that CE is equal to FE and EB is equal to ED? Well, that was my given right back up there. So the reason is given. Now step 2, CE plus EB equals FE plus ED. That's my addition property. I just took these up here and I added the CE and the EB together, and then I took the FE and the ED and I added those together. All right, so those got added, and CE and EB got added. Well, we know that CE plus EB is actually CB, and we know that FE plus ED is actually FD. So that is the sum, the whole is equal to the sum of the parts. The whole is equal to sum of its parts. Now, if we are actually going to do this in a proof, they allow you to sort of skip this middle step and go right from step 1 to step 3. And the reason that I write is just addition. So I don't go through the individual steps right here. Okay, but I wanted you to see the individual steps and how they're used. But it's sort of like a little shortcut that is allowed for us. Let's do another one with angles, and then we're just going to talk about vertical angles, and that's it for today, so it's not too long. So the angle one works the same thing. If you have angles and you add on angles, and the sum is going to be equal. But let's actually talk about subtraction when we're doing angles. And I can subtract with line segments also. But if equals are subtracted from equals, the differences are equal. Okay, if equals are subtracted from equals, the differences are equal. This one is a little bit harder because the thing we're going to be subtracting is going to be, it's going to be one thing that's going to be subtracted from each of them. You'll see in a second. So basically BAD, let's get a color. BAD, so that's this one right here that I'm tracing in red, BAD, okay, that angle right there, is congruent to angle CAE, which is right here. See how those, I got the purple angle and the red angle. They're overlapping each other, but they are congruent to each other. I want to prove that BAC, which is just this top part of the red angle, is congruent to DAE, which is this bottom part of the purple angle. Okay? Why would this have to be true? If the whole angle, the whole red angle, BAD, is congruent to the whole purple angle, CAD, all right, wouldn't the top part have to be congruent to the bottom part? Basically, it would have to be true because angle CAD, and let me highlight that, CAD is this, what I'm highlighting in orange right here. And CAD is part of both of those angles. So it would have to be true. Because angle CAD is part of the two congruent angles. When it's removed, so let's pretend we're going to remove that orange highlighted part, that angle CAD. When it is removed or subtracted, what remains will still be equal. And that is our subtraction postulate. So I have two big angles, and I'm subtracting out CAD from both of them so that what's left is also going to be congruent. So that's if equals are subtracted from equals, the differences are equal. How does that look like in a proof? How do I know that the measure of angle BAD is equal to the measure of CAE? Well, that was my given right here. So my reason is just going to be given. Now the measure of BAC plus CAD, so I'm just taking these two parts right here, BAC plus CAD is equal to CAD plus DAE. And that is the whole is equal to the sum of the parts. The whole is the sum of its parts. So I just took those whole pieces from statement 1 and I just broke them down into parts. If you can't see that, let me do them in different colors. So that's the orange, that's the yellow. So basically these two pieces equal the yellow and these two pieces equal the orange. And the reason is the whole is the sum of its parts. Now this is a new step for us. CAD is equal to CAD. Well, that's kind of obvious. Of course, CAD is equal to itself. We call that the reflexive property. And that's important, although it seems like, why would I even have to do that? But that is the reflexive property. Anything is equal to itself. The reason I have to do that is because I want to subtract CAD from the left. I want to get rid of this, and I want to get rid of this. Oops, I did the wrong one. I want to get rid of CAD from the left, and I want to get rid of CAD from the right. So in order to subtract it from the left and the right, it has to be written on the left and the right. So I say it's equal to itself, and if I was to subtract, look how I crossed them out in step 2. I crossed out CAD on the left, I crossed out CAD on the right. I'm left with BAC and DAE, which is exactly what I want to be left with, and that's called the subtraction property. Okay, so the thing that you want to add or subtract has to be part of the proof. So the way I get it to be part of the proof, if the same thing is being added or subtracted from both angles or both segments, the way I get it to be part of the proof is I just say that it's equal to itself. We didn't have to do that in the previous proof because the thing I was adding on was two separate things. All right. And this last one, we're going to be learning about substitution. All right. So substitution says that quantities equal to each other or to the same quantity may be substituted for each other. Now we've actually already learned that vertical angles are congruent to each other. I told you that, but this is the proof for vertical angles being congruent to each other. So I have two lines that intersect, M and N, and they're forming angles 1, 2, and 3. Now I actually have angle 4, but I don't need it for part of the proof, so I left it out. Given lines M, N, and N intersect to form angles 1, 2, and 3. So that's basically my given. So I'm going to write lines M and N intersect and form angle 1, angle 2, and angle 3. Given. Okay. Now, I'm going to help you with this. What is true about angle 1 and angle 2? Let me draw this purple line right here. See how angle 1 and angle 2 form a line? Well, that means angle 1 and 2 have to be equal to 180. So basically, the measure of angle 1 plus the measure of angle 2 equal 180. I'm going to hold off on the reason for a second, because I want to show you that here's another line, and angle 2 and angle 3 form that line. So the measure of angle 2 plus the measure of angle 3 also equal 180. Now the reason that you know that is that angles that form a line equal 180. Angles that form a line, and these reasons don't have to be word for word as long as they're conveying the same message. There is some, there's different words that can be used. It doesn't have, if you leave out one word, doesn't mean that you have it wrong. So angles that form a line equal 180. Now, can you see that both of these equal 180? Angle 1 and angle 2 equal 180, and angle 2 and angle 3 equal 180. Well, that means angle 1 plus angle 2 really equals angle 2 plus angle 3. Okay, both of these are equal 180. So basically, since angle 2 and angle 3 equal 180, I'm substituting it in over here so I'm replacing this 180 with angle 2 and angle 3. And I just used the reason is substitution. Equal quantities can be substituted in for each other. Since angle 2 and angle 3 equal 180, I'm just replacing this 180 right here with angle 2 and angle 3. Now they both equal 180, so they have to equal each other. Now let's look at what I'm trying to prove. I'm trying to prove angle 1 is congruent to angle 3, or equal to. I almost have it. Look, I have angle 1 on the left, I have angle 3 on the right. The thing that's in the way is the angle 2's. I need to get rid of the angle 2's. So the way I get rid of them is by subtracting them, but I can't subtract them unless they're part of my proof. So step 4 is going to make them part of my proof. I'm going to say angle 2 is equal to angle 2. Reflexive property. And I can just write reflexive. I don't have to write the word property. And then basically from step 3, I'm going to subtract them out, and I'm finally left with what I was trying to prove. Angle 1 is equal to angle 3. And that is subtraction. So I told you this last week or the week before that vertical angles are congruent. Look at angle 1 and angle 3. They are vertical angles. They are opposite each other. I just proved right here that they are in fact congruent.